Again, I promise that all this sigma notation is going to have something to do with antiderivatives eventually, but first let's learn some properties of our sigma notation. So this first one says if you've got the sum I equals 1 to n of a constant c, the answer is just equal to n times c. So let's put some real numbers in here to make this make sense. So if I had the sum I equals 1 to 7 of 5, this formula tells me this is equal to n times c, okay, which is our 7 times 5. It would be equal to 35. Think about what that sigma notation is doing. It's just telling you to take 5 and add it up 7 times for I equals 1, 2, 3, 4, 5, 6, 7. You're going to get 7 5s. It's equal to 35. Our second property of sigma notation says that if you have a constant multiple on a formula inside sigma notation, you can pull that constant outside the sigma notation, then evaluate the sigma notation independently and just kind of multiply it by c at the end. So let's say that we had the sum I equals 1 to 8 of 2i squared. That says that I can take that 2 and pull it outside the sigma notation. So I can say 2 I equals 1 to 8 of I squared. Then I could go ahead and add up all those 1 squared plus 2 squared plus 3 squared all the way to 8 squared. And at the end, just multiply it by 2. Next property of sigma notation is that sigma notation distributes over addition. So if you're adding up a sub I plus b sub I, you can just add up the a sub i's, add up the b sub i's, and then add them together at the end. Next property is very similar. If you have subtraction inside your formula, inside the sigma notation, then you can just distribute that sigma notation over the a sub I formula and the b sub I formula, evaluate them independently, and then subtract them at the end. This next property looks awful, but it actually helps us to split up a sum in a possibly useful way. So this one says, for example, if I had a sum, let's put some real numbers in here, from I equals 1 to 10, and let's say I'm doing I cubed as my formula. This tells me that I could make a stop off at an intermediate spot. So this says I could just make this the sum I equals 1 to 3 of the same formula, whatever it is, in our case, I cubed. And then I can pick back up at I equals 4 for my next sum, and then just add them together. So, and then go all the way to 10 of the same formula. So if you want to break it up, you can. You just take part of them in the first sum and part of them in the second sum. Here we have some sum formulas that don't look very helpful, but I promise they will be. This is helping you to cut out all those middle steps where you actually plug in all the values to a formula and figure out the sum. This kind of cuts to the chase and says if you're going to add up I for I equals 1 to a number, then you can just plug in that number into this formula and it will tell you for free what that entire sum is equal to. And likewise, we have one for the sum of I squared and I cubed. We are going to get familiar with our properties of sigma notation and these formulas in the pink box, and also see why we want to have formulas like the ones in the pink box. So here we have the summation from j equals 1 to 100 of this quadratic, j squared minus 4j plus 3. And think about how we would do this the way we did the examples in the last video. We would start off at j equals 1, 1 squared minus 4 times 1 plus 3. 2 squared minus 4 times 2 plus 3. And we would keep doing this all day long and into tomorrow until we got to 100 squared minus 4 times 100 plus 3. All right, so we're going to hopefully make this a little easier by using our properties of sigma notation and the shortcut formulas. All right, so I'm going to remember that sigma notation distributes over addition and subtraction. So this means that I can break this problem up into the sum j equals 1 to 100, j squared, minus the sum j equals 1 to 100 for j, plus the sum j equals 1 to 100, 3. In just a second, I'm going to show you what these pink box formulas are good for, but first I'm going to rearrange a couple more things. So I'm going to leave this first sum alone, j equals 1 to 100 of j squared. The second sum, I'm going to remember that constants can move in and out of sigma notation. So I can pull that 4 out front in front of my sum. So I can have 4 and then just have j equals 1 to 100, sum of j. And then the last one, we did an example of this one. If we're just adding up a constant, we had a rule that said I could just take that 3 and multiply it by 100. So it would just be 3 times 100. And think about what that sum is doing anyway. It's just telling you to take the number 3 and add it over and over and over again for j equals 1 through 100. So you're just adding up 3 100 times. So you get 300. Now we're going to use the pink box formulas to help us evaluate this sum. Remember that first sum, j equals 1 to 100 of j squared. We could evaluate that brute force, 1 squared plus 2 squared plus 3 squared plus 4 squared, all the way up to 100 squared. The pink box formula tells us that we can skip ahead to the punchline. So this sum is of the same form as this sum over here. Remember, the I and the j are interchangeable as the index of the notation. So this tells us that we can plug straight into that formula, n times n plus 1 times 2n plus 1 over 6. Our value of n is 100, so I'm going to plug that in. So the formula says to take n in the numerator, that's 100, then times n plus 1, 100 plus 1, then times 2n plus 1, 2 times 100 plus 1, that's 201. And then it says to divide the whole thing by 6. All right, next up, I've got another sum. This one, j equals 1 to 100 of j. That's going to be the same as I equals 1 to 100 of I. So I'm going to use that formula to evaluate this one. And that 4 is just going to go along for the ride. Okay, 4 times whatever I get from that sum. So I've got n times n plus 1. Again, our n is 100. So we've got 100 times 100 plus 1 divided by 2. And then at the very end, I've got plus 300. So again, just following along on our parts, that sum was equal to that. This is equal to that. And then I've got my 3 times 100 there at the end. All right, I'm just going to let my calculator crunch this out for me. So my first term is 100 times 101 times 201, all divided by 6. And I get a bunch. That's 338,350. Second fraction, I'm going to do 100 times 101, divide by 2, and then multiply that times that 4 coefficient. And I get 20,200. And then we've got that 300 hanging out at the end. So I'm going to do 338,350 plus 20,200 plus 300, and I get 358,850. Which was a lot of work, but it was certainly a lot easier than trying to plug in j equals 1 to 100 at the very beginning of the problem.